All right, so the last section was about the dot product. The dot product was taking two vectors and making a product in such a way that we ended up with a scalar when we were done. We did that using component-wise multiplication and summation when we were finished with that. So we're going to look at another kind of product for vectors today, and this is called the cross product. And I'd like to give you some kind of an idea of what it actually is doing when you're finding a cross product. So many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal to two vectors. Here we will study the product that will yield such a vector. And obviously by the title header, you know what that product is called. It's called the cross product. Your book actually takes a little bit different approach than the last book that I used to teach this. And I like what I did when I did it the last time I taught this, and I think for those of you especially who are involved in linear algebra, this will be an easier way to think about it. So I'm going to go with what I've done before instead of how your book presents it. So if you absolutely hate what I'm doing, you can see another version of how to think about it in your book. They're equal, they're equivalent, I mean they work just fine, but this actually does it from a linear algebra sort of perspective, okay? So I'd like for you to think about what you remember, for those of you who are in linear algebra, or maybe if you have seen this in a different course, about determinants. Determinant. I don't even think I said it right. Determinant. I didn't spell it right. There we go. And we're going to start with a real simple one, a 2 by 2 matrix. The determinant of a 2 by 2 matrix, and I'm going to put the components in here, A1, A2, B1, B2. So can somebody tell me what you remember about the determinant of a 2 by 2 matrix? What would it be? A1 times B2 minus A2 times B1. And for those of you who maybe aren't in linear algebra or haven't seen this recently, what we're doing is we're multiplying along the diagonal that's top left to bottom right, and then you subtract and you multiply along the other diagonal up here, okay? Does that sound like things we've seen recently or remember in the distant past? Is that all good for everybody? Okay, so that's a 2 by 2 matrix. It gets messier with a 3 by 3 matrix. And I'm only going to present the determinant of a 3 by 3 matrix in terms of what we need to do with it, not in terms of all the different ways you could calculate it, okay? Because there's more than one way to do this, but we're just going to be focusing on one of them, so I'm just going to present that one. Okay, so the determinant of a 3 by 3 matrix, and I'll just do it right here. I'm going to put the same A1, A2, A3, B1, B2, B3, C1, C2, C3. And I don't want to go too far down the road of linear algebra here, but let me show you what we're doing. We're going to take the top corner and we are going to expand along that value. So, and I don't remember all the details of the language, so I'm probably butchering it. Please don't tell Dr. Marsh on me.
Okay.
But what we're going to use is we're going to use that row, that column, and that makes a 2 by 2 matrix down here that's not neither on that row nor that column, and we find the determinant of that component. So this is A1, and then it would be B2, B3, C2, C3. And then we do the same thing with the next row and column. I don't know if I can do it here. I'm going to have to delete that. So here's back to A1. And I'm going to go to A2. Okay, we're going to expand along the top row. So A2, and you actually need the opposite sign, so it's subtraction of A2, and you again look at the rows and columns that are not going to be connected. Oh, what did I do there? Connected with A2. So on A2, if you were looking at the rows and columns A2 is in, you would sort of be ignoring those pieces, and the determinant would be found with the pieces that are not ignored. So it would be the B1, the C1, the B3, the C3. So over here, I would have B1, B3, C1, C3. And then the last column along my top row has an A3 in it. It is addition on that one. And so we're using this A3, which again isolates this row and this column from being involved. And I have B1, B2, C1, C2. And I use the determinant for those.
Does it matter on the second term whether you write the B3, like the B3 and C3 in the left-hand column, and the B1 and C1 on the right side?
Say that again. I actually wrote something in here wrong, but say it again. Oh, no, that's okay.
You're looking at A2.
Yes.
Times, does it matter that you wrote the B1 and C1 on the left-hand side and then the
Yes.
B3 and C3?
If you switch the order, you're going to get the wrong sign.
Okay.
So it's quite possible that if you've learned it in a different way, maybe they put an addition sign on your A2 and they switched those two rows, which would have compensated. It would in effect do the same thing. So you may have seen it done differently. Everybody learns differently, and I recognize that fact. I'm a very visual learner, so to me, when I look at this, I see the images and how to cancel out the rows, and that resonates with me, and it helps me to remember it. And so your book does this totally from an algebraic sort of formula perspective, and that doesn't help me to remember. So this is one of the, from another book that I've used, and I think it does a very good job with the visual. If you take this and expand it a little further, of course, what will happen is you get all of those determinants that you had from the 2 by 2s right here, right? They're going to expand. So I'll write it out because that's actually all your book does is it writes out the next formula I'm going to write down as the formula and goes from there. But if you like formulas, that's great. That's fine. But this would be A1 times, and then it would be B2, C3 minus C2, B3, and then minus A2. And I'm just using diagonals, right? I'm going down, and then I'm going back up with subtraction. That's how I'm doing on all my diagonals. So this would be B1, C3 minus B3, C1. And then I have plus A3, and it would be B1, C2 minus B2, C1.
Are we ever going to do anything larger than the 3 by 3s?
No, because we're still working with vectors in 3 space, so no. Yeah, our vector analysis is done with 3 by 3s. I'm sorry, we're not. We're going to stick with our 3D vectors. I can write out this long, ugly expansion. That's actually where your book, puts us at a formula. I think the picture that I can create from the determinant above makes more sense to me. So whatever works for you is fine with me. And we're going to do one because there's a lot going on in here. Let me tell you one more thing before we do one. We're not going to do a determinant directly. We're going to actually do it in terms of what we care about using, and that's about the cross product. So let me actually tell you how these determinants relate to our cross product. So for 2 vectors, U, which is component-wise U1, U2, U3, and V, which is component-wise V1, V2, V3. The cross product is U cross V. And so you'll notice, I think I did it when I was in the last section. I was thinking about this today when I was thinking about the way I say my language here. I will always say U cross V here. And I think I said U dot V every time I did it when I was doing dot product. Because if we say multiply, or times, we're left wondering which one we're talking about. So I will be on my best behavior to say cross on this one and dot when we're doing a dot product. And it looks like this. So the determinant that's created is I, J, K, and then it's our unit components for the U and the V. So U1, U2, U3, and V1, V2, V3. Okay. So if I write that out, I end up with I times the unit component U2, or the determinant, excuse me, of U2, U3, V2, V3, minus J times the component U1, U3, I said U and I wrote V, U3, V1, V3, plus K times U1, U2, V1, V2, like this. And we'll do an example. We're going to find 3 different cross products. We're going to find U cross V. We're going to find V cross U. And we're going to find, that's like B. And we're going to find V cross V. And our U that we're going to work with on this example is going to be 2, negative 2, 0. And vector V is 3, 0, 1. So to start with, we're going to do U cross V. Okay, so maybe I'll do it on the first one. I'll go ahead and write the big 3x3 determinant out so that we can expand along it. If you don't need to see the big 3x3 and you can jump immediately into this version of it, that's fine as well. So it doesn't matter to me, but I'll write the first one out just in case it helps you to see. So we're doing IJK. We have 2, negative 2, 0, and 3, 0, 1.
So I, J, and K are not actual numbers, they're just...
They're the vector component hats, yeah. The directions I, J, K in 3 dimensions.
Okay.
Yeah.
1, 1, 1.
Yep.
So are we turning 2 vectors into a 3-dimensional
We are,
space?
no, we are creating a vector that is orthogonal to the 2 vectors we started with.
Okay, gotcha.
So if you kind of can imagine 2 vectors, as long as they're not, 2 vectors that they would lie in the same plane, right? So the 2 vectors that lie in the same plane, and you can shift them, right? We can move them around to an equivalent form, and they meet up at a corner. So if you can imagine a corner of like our classroom along the floor, and you have 2 vectors that are meeting up in that corner, they don't necessarily need to be the walls, if you will, but they could be. Then the orthogonal vector to them would be the wall that's going straight up, right? That idea. Okay, so give you sort of a little bit of an imagery. We'll talk about in a little bit more what some weird things are that can happen with that description, but that's the basic idea. We're creating orthogonal vectors. Okay, so we are going to expand along the top row. So I have I, and I have the vector negative 2, 0, or sorry, the determinant negative 2, 0, 0, 1, minus J, And these are I hat, j hats, okay? And then they're unit vectors. That's what those symbols mean. I haven't used them because we haven't really needed them exactly, but they are present when we're talking about ijk. 2, 0, 3, 1. And then k, and I have 2, 3, negative 2, 0. Like so. Okay, I'm going to finish at least this part of this one on here on this slide. Okay, so for the first one, I have I hat, and very nicely, part of this is 0. We do have some zeros present here, so I only have this diagonal, so that's negative 2. So it's negative 2i. I have minus j. Again, I get some zeros. Only this piece actually gives me a number. The other diagonal gives me a 0, so I actually have minus 2j. And I have another 0. That one's 0 right here, so this one's the only one that gives me a value. And I have subtraction of that, so subtraction of negative 6 gives me a positive 6k. Yes, sir?
And does the cross product equal the matrix, or do we have to specify that equals?
When you do the straight bars down, looks almost like absolute value, that means determinant. Matrix has the parts that look like brackets. This is what you would mean if you had values inside of a matrix. Without the, this component piece of it, basically, this part, it means determinant. Good question.
What?
Well, up here on this notation here means determinant. If I actually meant matrix, it would look like this. So I'm not talking about the matrix, I'm talking about the determinant of the equivalent matrix or the corresponding matrix. The notation is already present by the symbols that are being shown with those vertical bars. Is that okay, Chris?
Yeah.
Okay. All right, any other questions? We're going to do the next part, which is V cross U. Okay, I need to move these to the other screen. Yeah, I don't think I got it. Okay, so we're looking now for V cross U. So again, maybe you want to see the whole determinant. You could do that. That will be fine. They'll go in a different order, right? The row in the middle would be my V row, and the row at the bottom would be my U row. Or if you don't need to see it, I'll draw this one out differently so that we can actually think about it from that perspective of maybe not drawing those out. If I am working on V cross U and I've got the I component, then I'm working with these rows because these are not the rows that would be I. So these are going to create my determinant with V along the top. So it would be 0, 1 from V and negative 2, 0 from I. I'm sorry, from U. Minus J. Okay, so with J, that is the second component. Like X, Y, Z, it would be the Y. So we're looking at the first component and the third component of each of U and V. V is along the top, so that's 3, 1. And then U is along the bottom, so that's 2, 0. And then plus K. So in the form of K, we're using the third component. We're not using the third component. So we're using the first two components of each of U and V. V along the top, so it's 3, 0. U along the bottom, 2, negative 2. Does everybody see where all the pieces came from? We good with that?
It's just the negative of V cross U, negative of V cross U.
Yes, it is. And we're about to find that out. You're spoiling all the fun, Kyle. Man. All right, so let's take a look. Yes, this is 0, right? And then this component would be negative 2. And so I have subtraction of negative 2, so I have a positive 2i. Did you have a question, Bryson?
Yeah. Why
did we put the V vector on top of the U vector?
Because we're finding V cross U this time instead of U cross V. Yeah. Yeah, and we're doing it for the express purpose of what Kyle already spoiled the fun about. I mean, in recognizing that it has a relationship to U cross V. Yeah, so this is 2i, and then I have, this one's 0, but this piece right here would be 2, and it would be minus 2, and then I have another minus right here. So I end up with plus 2j. And then at the end, this one's 0. So I only have this component, which would be negative 6, so I have negative 6k. And Kyle's exactly right. This is the same thing I got before, but the opposite sign. So this is the opposite, or the additive identity, if you will, or whatever. It's the negation of u cross v. I'm about to give you a property list, and that's going to be one of them. What's that?
Can I spoil the next one?
No, you can't. I would like for you not to spoil the next one. And don't anybody else spoil it either if you don't know what I'm talking about yet. All right, so we're going to do v cross v. So to do v cross v, we would have I, and we're going to put both components of v that are not in the I spot, which would be 0, 1. So 0, 1, 0, 1, plus j. Again, both the components that are not in the j spot, the middle spot, which would be 3, 1.
Isn't it minus j?
Minus j. It won't actually matter, but that's okay. It technically is minus j. Shh. 3, 1, 3, 1, and then plus k. And I would have 3, or 0, 1. No, wait. What was it? 3, 0. 3, 0.
Can I ask a question?
Yeah.
Is it because since they're both in the same direction, there's no degree, no angle?
Yeah, that's what's going on. And I've got some properties to list, and there's more about angles going on here in a minute, too. So I think you guys already saw that you're getting zeros everywhere, right? Yeah. So this is the 0 vector. So it'd just be the vector 0, 0, 0. It is a vector still, right? Not a scalar. I'm not getting scalars here. I'm still getting vectors. So there are some properties we're going to list out. These are algebraic properties of the cross product, and 2 of them are the 2 we just discovered. That when you do, there's not a commutative property, right? But when you switch the order, there is a relationship between what happens, and that a dot product with it, or sorry, a cross product with itself actually gives us back the vector 0. So let me highlight for you a few of the other products or properties as well.
Is that because the angle between them is 0 and the cross product is magnitude A, magnitude B sine or theta?
We will get to that as well. You guys are really just all over this today. Algebraic properties of the cross product. I'll leave that part off, but that's what it's for. We're going to let u, v, w be vectors and c a scalar. And just like when we did the dot product, there's a lot of properties here. The first one is the one that we saw early on already, that u cross v is equal to negative of v cross u. It's kind of a nice fact. In terms of something that looks like a distributive property, if I did u cross v plus w, that actually equals u cross v plus u cross w. We saw a similar version to this next one last time as well, c times u cross v. You could either multiply the scalar c by u and then cross it with v, or, sorry, let's say equals, or you could multiply the scalar times the vector v and then do the cross product with u. If you multiply the vector u times the 0 vector in either order, what do you suppose you get? The 0 vector, right? But that's not the only way to get the 0 vector, as we have already discovered. When you do the cross product of a vector with itself, you also get the 0 vector. That's an interesting property that doesn't happen with, say, addition, right? Everything in addition has a unique additive inverse, and this has an inverse sort of feel to it, but it's not unique. And then the vector u dot product with the cross product of u and w, or v and w, is the same as taking the cross product with u and v and doing it with the dot product of w. And you'll notice nobody's switching any orders around. There's no other versions of this where I can then swap letters in different orders or anything like that. The orders stayed the same. These are algebraic properties, and I'd like to put the geometric properties with these next, and then we'll have to stop for today. So let's get the geometric properties written down, and then we'll push pause. So theorem 11.8 are geometric properties, ones that everybody keeps bringing up. So you got to have them down before you keep talking to me about them. Let u and v be non-zero vectors in space. So we'll just say non-zero vectors. And theta, the angle between them. Property number 1 is that u cross v is orthogonal to u and v.
Is there like a symbol for orthogonal?
If there is, I haven't seen it used. I mean, we'd love it to look like the perpendicular symbol. I mean, that's sort of our imagery that we've had in mind, but I haven't seen anything used to that extent, so I'm going to go with no. The magnitude of u cross v, okay, is equal to the magnitude of u times the magnitude of v sine theta. Two more. We've seen this one. U cross V is equal to 0 if and only if U and V are scalar multiples. What does it mean for them to be scalar multiples? They're parallel. That's another way of saying that same fact. If we have parallel, then we're not going to have any angle between them like you're describing, right? And the last one is that the magnitude of u cross v equals the area of the parallelogram with adjacent sides u and v. So if you take u and v, if you make them adjacent, right, so you're shifting them into the plane wherever they need to be, they will create a parallelogram with those components, and the area of the parallelogram is equivalent to the cross product's magnitude. And we'll pick up there next time.